Hello students, we are meeting for our next lecture of cement and glass industry, and in the last lecture we have seen how actually cement is manufactured and what is the treatment to the clinkers and then special types of cement, and we end up at the uses of cement. Now today we'll see how what is the setting and hardening of cement, means when cement is used for construction purpose, actually what chemical changes takes place while it becomes the hard cement. Okay, so there are two processes. First is setting of cement. So when water is added to the cement, first the anhydrous compound dissolve and precipitate of less soluble hydration products are formed. Okay. Now the plastic mass of cement passes to the hard condition in two stages. Means initially the solution paste kind of solution which is formed, that is a plastic in nature, and that becomes hard in two steps, that is setting of cement paste and then hardening of cement. So first we'll discuss the setting of cement. So this setting of cement powder, when it is mixed, cement powder when it is mixed with water, it gradually converted into solid mass. The mass becomes hard, tough, and resistant to pressure. So it is known as setting of cement, means conversion of this powder cement after addition of water to the hard material, that is called setting of cement. And formation of this hard rigid mass takes place by series of complex reaction that we are going to discuss. Although there are many theories which are proposed, what is the actual action, chemical changes that are taking place. In that, first is selective hydration theory. So out of the three constituents of the cement, C3S type of cement, that is tricalcium silicate, is quick setting. A hydraulic reaction does not always proceed to uh, completion. So what are those reactions? The reactions are like this. Okay, so tricalcium silicate, then dicalcium, then again 2 moles when monocalcium silicate. All these reactions with water takes place like this, converting to it to calcium hydroxide and calcium silicate. Okay, so thus the strong mass contains hydrated silicate with some crystalline calcium hydroxide. This is the calcium hydroxide in the crystalline form. The first setting takes place within 24 hours. Okay, the Portland cement containing dicalcium silicate, that is C2S type, sets very slowly, while tricalcium aluminate C3A type sets quickly, but product has little strength. Means depending on what are the constituents of the cement, as discussed in our types of cement, this kind of reaction takes place. The new compound produced separates in crystalline form. Okay, and the cement becomes strong. The strength of cement is due to interlocking of minute crystal deposited from supersaturated solution. So when water is added, it becomes hard because of interlocking of these minute crystals which are formed and they get deposited. So this is the one theory, that is selective hydration theory, that suggests the formation of hard mass. There is one more theory, that is colloidal theory. In this, according to this theory, action of water on cement brings about two types of reaction. Okay, so first a solution of lime, aluminates, and other compounds of cement is formed. Means when water is added, this solution is formed, and the calcium hydroxide and other product pass into solution. Means this calcium hydroxide and they get dissolved in water and form the solution, and separate again in the colloidal or gelatinous form. Means again they are not forming the homogeneous solution, so they get separated as colloidal or gelatinous form. The gel fills the pores of cement and make the cement impermeable to water. Means water get occluded inside and it does not allow water to get outside. The gel subsequently dries up, hardens and binds the grains together. So that is the role of this gel. This gel is responsible for hardening of the cement, and the process continues for 10 to 20 days, and within 10 to 20 days the mass becomes very hard, and the various components of cement that contribute to heat are like this. Means C3A, tricalcium aluminate, gives out a large amount of heat. Then next is C3S, then C4AF, and then C2S. Means C2S gives the least energy of hydration, and C3A gives a large energy of hydration. Electron microscope study reveals the presence of fibrous mass of calcium hydroxide and rhombic slabs of hydrated dicalcium silicate, hexagonal plates, and needles of hydrated tricalcium elements. So these are the formation of fibrous calcium hydroxide and rhombic slabs of hexagonal dicalcium silicate, hexagonal plates, and needles. They are detected by electron microscope studies. So the reactions which are taking place are like this. Is here you can see these crystals of calcium hydroxides are formed, and the water hydrated colloidal gel is formed, and that water is not allowed to go outside, that is it becomes impermeable, and later on this gel is responsible for hardening of the cement. Now contribution of the compounds, there are various components of the cement that we know, that is C3A, C3S, C4AF, and C2S. Now depending on various types of cement, there are various compositions of these components. Okay, now depending on this, what is the contribution of each compound to the strength of the hard material that is formed, it is given in this table. So on first day, what are the responsible components, and slowly up to the 2 years how it is going to change. So in this way, by these two theories, how the setting of cement is explained. Okay, now there are some factors which decide the setting of cement. So what are those factors governing the setting of cement? In that, first is retarder. Retarder means which are against the setting of cement. So what are those? There is first is gypsum. Okay, so gypsum acts as retarder in cement, which reacts with C3A, that is tricalcium aluminate, and it forms a calcium sulfo aluminate. Okay, now its crystalline form has various numbers of waters, that is it ranges from 30 water molecules to 12. So there are different hydrated calcium sulfoaluminates are formed, and these compounds have very low solubility in water. Okay, and the process of sulfoaluminate formation proceeds until lighter gypsum or C3A is exhausted. May either one of them, either gypsum or C3A. And during this time, C2S, that is dicalcium, tricalcium silicate, dissolves in water and slowly precipitates out as C3SH. Okay, the slow setting of C3SH thus decides the structure of cement. Means due to gypsum, the setting of C3S get prolonged. So that is the problem. So that is the role of retarder. Okay, so depending on the requirement, we can change the quantity of gypsum. So here there is one graph which explains the uh, with as the time proceeds, how there is a rise in temperature for various types of cement. That is, if it is a high alumina cement, obviously the temperature rise is very high compared to hardening Portland and normal Portland cement. The next factor is rate of cooling of clinkers. Means while making the cement, after conversion, after fusion of argillaceous and siliceous material, clinkers are formed that were discussed. So depending on the cooling rate of clinker, that is very important. So due to slow cooling of clinker, alumina and iron oxide form the melt form tiny crystal. Okay, and due to quick cooling, the whole liquid solidified into glassy mass. So these are the two changes. Slow cooling gives tiny crystal, while fast cooling gives you glassy mass. So slow cooling produces needle shaped C3A hydrate in a very short time. Fast cooling does not produce such crystal on hydration, so it forms the film of dark amorphous material surrounded by cement grains. So that is the also affects the rate of your setting. So setting is affected by rate of cooling of clinker. The next is concentration of calcium ions. So calcium salt increases the solubility of calcium silicate and decreases the solubility of calcium aluminate. So that is the role of calcium salt. So the pH of solution is reduced so that precipitation of hydrated calcium aluminate is prevented. Okay, and the precipitate of aluminum hydroxide is formed. So the presence of calcium salt also affect the setting because it changes the solubility of calcium aluminate and calcium silicate. And also along with that, if there is a presence of sugar, boric acid in cement brings about quick setting. So these materials produce salts with passage of time, so which are slightly dissociated. Okay, so that is the role of concentration of calcium ions. Then next is iron content in clinkers. So what is that iron content in clinker? The presence of iron has influence upon early reaction of setting. Okay, so if iron is there, it affects the early reactions of setting, but gradually iron is precipitated as gel, which forms protective film around the clinker grain. So this film retards the continued hydration of compounds. So hydration, that is setting, it get affected due to iron content in the clinker. Now along with that, there is one important part, that is false set. Means we may feel that it is set, but it is not, cement is not set. So this abnormal type of set is called as false set or immature stiffening. So in this set, rigidity in the paste is developed in few minutes but without evolution of appreciable heat. So heat is expected to release, but it is not observed in case of false setting. So when such stiffened paste is remixed with further addition of water, it resumes its plasticity. So when to avoid this stiffened paste again remixed further with addition of water, and again it can resume its plasticity, and it removes the false setting. So that is the false setting of the cement. Then this is all about the setting of cement. After setting, the mass becomes hard. So that is called as hardening of cement paste. Okay, so it is further progress of chemical reaction involved in setting of cement, and because of this process, the paste acquires the characteristic necessary for the development of strength. Okay, so what are those characteristics? And that is durability and in the concrete structure. So these properties necessary for hardening are developed in the hardening process. So in that, first is hydrolysis and hydration of cement. It is found that C3S tricalcium silicate is hydrolyzed to 15% in a day, 23% in 7 days, and 26% in 6 months. So this hardening process is prolonged process than the setting process. So beyond this period, no further hydrolysis is observed up to 2 years. Okay. So similarly, the amount of water combined with C3A tricalcium aluminate at 1 day is 30%. It increased to 35% in a month and 38% at 2 years. So this figure shows the rate of development of compressive strength with time. So on x-axis there are number of times a days. So for a year you can say this graph is plotted and how compressive strength is developed. So in C3S cement, the strength is very high, but it is not quick setting. C2S little less, then then 5 CaO eliminate or 3 CaO eliminate, that is C3A is the least having least strength because it is quick setting. So quick setting is exhibit low compressive strength, while as slow setting exhibit the higher compressive. So the introduction of 50% of C3A is found to raise the strength of C3S up to 3. Okay. So this is all explained in this graphical form. The next is depth of this hydrated water. It is observed that depth of hydrated layer in a typical Portland cement clinker was zero point 0.5 microns in 28 days, 5 microns in 90 days. So addition of gypsum increases the penetration of hydrated layer. Means as the water get penetrated inside, more strength will be developed. Then next is effect of composition. Tricalcium silicate is mainly responsible for the strength at early stage, and its effect becomes negligible beyond 1 year. Solution of magnesium oxide, that is 10%, or calcium oxide in a raw mixture reduce the strength sharply with increasing percentage of magnesium oxide. So magnesium oxide decreases the strength of that same. So increase in C3A and C4AF content lowers the resistance of concrete. Okay, so if C3 and C8AF are increased, it lowers the resistance of concrete. The presence of small amount of phosphorus pentoxide in clinker reduces the strength of cement. So this is one also you can say uh, retarder. And when the percentage of phosphorus pentoxide is more than 2.25%, it becomes useless. So phosphorus pentoxide should not be in more quantity. Then effect of cooling rate. Slow cooling of clinker produces crystalline tricalcium aluminate, while fast cooling produces glassy phase. Okay, so that were discussed in case of rate of cooling of clinkers also. So cement having more glassy phase produces satisfactory plastic paste. Okay, which develops good strength. So fast cooling gives you glassy phase, which is required for this uh, development of strength. Okay. Now the last point from the this is all about the hardening of cement. Okay. What are the hydrolysis reactions, up to what depth it water goes, what is the composition, and rate of cooling are the responsible you can say factors for hardening of cement. Then the last point which you must have heard many times, that is reinforced concrete, that is ferro concrete. Means here RCC construction you must have heard. What is RCC? Reinforced concrete, cement concrete structure. So what is that? While building the cement construction, if you are using steel frame, so whenever there is a centering, means when there is slabbing process goes on, first network of that steel material is developed, and in that cement is poured, so that the after hardening of that cement, it gets the very large strength because of that steel network. So that strength is reinforced because of use of iron network, that is iron rod network. That's why it is called as ferro concrete. So concrete is brittle, it cannot bear tensile load. Similarly, steel alone is not very resistant to weather. Hence, it is necessary to reinforce the concrete with material which can support the tensile load. So, steel rods with rough surface are generally used in reinforced concrete. So, that gives the strength to the construction. So, this completes our first part of this chapter, that is cement. Okay, now we have completed the cement part. Now we'll stop here. We'll meet in our next lecture for next topic. Okay, thank you.